Alright, and we're live. So I'm pretty sure you've already seen the question for today at some point, just because there's only so many Taylor series, and I was trying to hit all of those Taylor series earlier on. We'll take another look today. So our goals are to determine the first four terms in general form of a Maclaurin series, the convergence or divergence of an infinite series at those bounds, and then determine the error bound of the Maclaurin series approximation. Ooh. And I'm cutting this off a little bit, so let me break this out. Try that. Sorry. Okay, so for this one, we've got the y value at 0, first derivative at 0, and then the n plus 1 derivative at 0 after this. The function has derivatives of all orders from -1 to 1. And the derivatives satisfy all of those conditions above. The Maclaurin series converges for all x's that are less than or equal to about 1. So I want to show that the first four non-zero terms are these four terms, and then write the general form of the series. What do we have to do first?
So we have to find the first four derivatives.
Okay.
So we already know first two. So the next one is, if we plug in 1, then it's f 2 derivative is equal to minus f1 0, so that's -1.
Okay, so we were told that the first derivative is at 0 is 1. So if that's true, let's write a general form instead. So for a Taylor series, I'm going to sum up what?
Fn 0
Okay, so for us that'll be 0, but
x,
I'll do this for now.
x minus a.
Okay, so if you want to center it, sure.
And x minus a to the nth power over n factorial.
Okay, so right now, going from n equals 0 to infinity, we're going to go from n equals 0 to 4. So when n is 0, this would be the 0th derivative, which is 0 times anything is 0. So our first term is 0. Okay, second term. What's my first derivative?
1.
1? Okay, so I've got 1x to the first power over 1, which is just x. Okay, then for every next derivative, we'll have negative n times the derivative at 0, so the previous derivative at 0. So if that's true, our n is now 2, right?
Yeah.
So that'll be our previous term, n to the first power, times negative n. I guess that's going to be n equals 1 for us now, the way that they've set this up. So we should get the second derivative, right?
Mm-hmm.
I guess that is a little bit confusing. Here I've got a separate n than the one that I'm using here for our Taylor series formula. Because I'm plugging in the n plus 1 derivative, whereas this one I'm just plugging in the derivative. Okay, so for now, n is 1. If I do, then that'll give us the second derivative. Will be the previous derivative, which is here, at x times negative n.
So -1.
Okay, negative 1. The second derivative at 0 is negative 1. And then with our Taylor series formula, what's going to happen?
It's -1/2.
Okay. Negative x squared over 2 factorial?
Plus 2 plus 2 is 2.
Okay, it is 2.
So 2/6, that's 1/3.
Okay. And the last one?
So 3, -6. So -6 over 12.
Right.
No. Yeah, -6 over 4 factorial.
Okay, so that's 6
So
over...
that's,
Oh, you're right, not 12. That's 24.
yeah.
Okay.
So 1/4.
I'm going to write our intermediary step here. So that might be worth a point. So this was 2, 3 factorial. 2 factorial. Okay, so that leaves us with x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Alright, what's the general term of the series? So if this kept going. Wait, I can't erase that, can I? Oops.
So it's just simple. n-1, n plus 1 power.
What are you raising to the power?
-1 to the n plus 1 power.
Okay, so that'll start even, which is positive. This looks good.
And x to the nth power over n. Yeah.
Okay. I want to know whether the Maclaurin series that we just created converges absolutely, conditionally, or diverges at 1. So I'm going to copy this general form.
Yeah.
Okay. So at x equals 1, will it converge absolutely, conditionally, or diverge? What do we have to do?
So we have to plug in 1.
Okay. Negative 1 raised to the n plus 1 times 1 raised to the n over n. What's 1 to the n power?
That's just 1.
Just 1. Okay, we're going to sum this up forever. 1 equals 1 to infinity. So this is still going to alternate. I've got negative 1 to the n plus 1 causes us to alternate of 1 over n. So if we do, will this converge conditionally, converge absolutely, or diverge?
It will converge conditionally.
That's right. So it'll converge conditionally because we are alternating.
Yeah.
So it converges conditionally by alternating series test. Okay. And then we want the first 4 non-zero terms in general term for the integral from 0 to x. I'm going to go back to our first 4 terms, I think. Oh, wait, they've got it here. Never mind. So while I'm doing this again, what's going to happen for our terms for the integral?
So if we integrate it, then that's 1 over x. And 1 over 2x squared minus x cubed over 6 plus x4 over 12 minus x fifth over 20.
Okay. Do you see the pattern?
Yeah, it's like 1, 2, 2, 3, 3, 4.
Okay. So can we write it?
So negative 1 n plus 1
Okay. x2
and x plus 1
n plus 1. Okay. Over
and n plus 1 and n.
Okay, that's good. Last one. We have an nth degree Taylor polynomial for g, which is centered at 0 and evaluated at x equals 1/2. where g is defined as the function we just made in part C. I want to use alternating series error bound to show that the fourth polynomial approximation minus g at 1/2 is less than 1 over 500.
Mm-hmm.
Okay.
Mm,
Okay, let me go back because we were just looking at the first 4 terms last time, right?
yeah.
Okay, so the first term that's not used will help form our error bound. Now, since we're looking at the 4th degree polynomial approximation, that means the fifth power term here is what's not going to be used. Okay, so what happens if I plug in 1/2 into our 5th term, the first term that's not used by our 4th degree polynomial?
So n is 5, and you plug in 1/2.
Okay, so that'll end up being this term over here, right?
Yeah.
Okay, so that's 1/2 to the 5th power over 20. The error is bounded by the first unused term. Or negative 1 over 5 to the 5th power over 20, which we had from the last page. Negative 1/2 to the 5th power over 20. Okay, if I raise this to the 5th power, what's going to happen?
That's 1 over... It's very small number.
Sorry. I got this wrong, actually. We're plugging in 1/2, not 1/5.
Yeah.
Okay, what's 2 to the
So
5th power?
25, 1 over 32 times 20.
Perfect. So we are bounded by 1 over 32 by 20. How much is 1 over 32 by 20?
It's just very small. 640.
Yep. Okay, and we were trying to prove that the error is going to be less than 1 over 500. Is this error less than 1 over 500?
Yes.
Which is less than 1 over 500. Okay. So we could say something like this. P4 1/2 minus G 1/2 must be less than 1 over 640, which is proved. Which is already less than 1 over 500. Okay. Any questions on what we did?
Nope.
All right. So for homework, we've got questions 4 and 5 from this. Coming up, you've got, I believe you've got course sites or AP Classroom work for physics already. It's due on Wednesday at midnight.
Or yeah.
I don't think we did the same for Calculus BC. I think I'm going to wait until after the physics one to assign one from AP Classroom for Calculus BC. So we're going to stick to this for now. But you will have some AP Classroom work later this week for Calculus BC.
Mm-hmm.